this lesson, we will focus our attention back to working on the network layer. And so we want to keep in mind that the network layer is used to send packets back and forward from the transport layer to an appropriate destination. And so at an essential level, we could bundle this function within the transport layer, but that's not necessarily a good idea. You want to recall that IP routing is going to happen here. And so how does a router know what route to take in order to transport an appropriate packet? So here we have an example of messages that need to be routed from one source to one destination. And if you recall, at our source and destination hosts, we have the application layer, the transport layer, the network layer, the link layer, and physical layer. While at our routing devices, we have the network layer, the link layer, and the physical layer. Now we can serve to see that there may be many different connections that connect these host devices. So there can be wired as well as wireless connections, as well as different hosts that can be utilized in order to, or different routers that can be utilized in order to reach an appropriate source and destination. So with these intermediate hops on the network, we don't necessarily need the transport layer functionalities because the nodes are simply going to forward the packets to the destination without affecting the network. And so we want to consider the network layer. We have our routing information protocols. This can include the link state protocols, distant vector protocols, as well as hierarchical routing and addressing as well. So we refer to this layer as the network layer because it provides for a separation of responsibility and allows the transport layer to be independent of any addition or deletion of the network connections to a host. And so with this in mind, we'll have the destination address and the packet size parameters being utilized as being able to interface between the transport and network layers. So let's consider also the intuition behind routing algorithms that we can utilize to determine the path that it should take to route a packet from a source to an appropriate destination. So in this case, we want to consider that we have various nodes that are labeled A, B, C, D, E, and F. And our basic question here is we want to understand what is the distance that it will take in order for us to reach a certain node. And so with this in mind, you want to consider that the network is going to amount to a collection of various hosts and routers that we're able to connect to using a unique IP address. So if we consider that the network is going to be fully connected, then what we want to take into account is the route that would be most efficient for a packet to take to reach from one source to any destination. So we want to assume that the cost of sending a packet between any two nodes is the same, but in reality, it's not going to be the same. the cost of sending a packet between a point A to point B or point A to point C is going to be denoted as a cost. And it's basically a metric that we can use to determine the time it might take to move between two hosts. So one routing algorithm that we can consider is Dijkstra's shortest path algorithm. With this algorithm, we're going to use the global information that is available in order to determine the path, the cost between nodes. So this requires n-1 iterations, and we'll have at least one cost route to a destination. And it can run simultaneously on each node. So if we want to calculate the cost on node A, during initialization, we have the cost to be from A to B to B2. We have the cost of 1 from the route A to C. And then we have the cost of 4 from A to D, and a cost of 5 from A to E, and so forth. Now let's consider our costs for nodes from A to C. So first we consider from A to B to be the same as our cost from A. The cost from A to C is going to be 1. The cost from A to C to D is going to be 3. And the cost from A to C to E is going to be 4, while A to C to F is going to be 6. We consider another cost for A, C to B. With the shortest path from A to B is going to just be 2 for A to B. For A to C, we have the same. From A to C to D, we have a cost of 3. For A to B to E, we have a cost of 3 as well. And we have the same cost of 6 for A to C to F. And other nodes for the least cost routes known from A, C, B to D, we have A, C to D is going to be 3, as well as A, B to E is going to be 3, and A, C, D, F is going to be 4. And so we can round out our final routes for A, C, B, D, E, where we have a cost of 3 from A to B to E, and 4 from A to C to D to F. And then for our final route, we have a cost of 4 from A to C to D to F as well. And so let's consider the distance vector that we have in action. You want to consider that it uses neighbor information and local algorithms. So that means that every node only sees its neighbors. Each node knows the cost to each of its neighbors. Each node is going to send its idea of routing to each of its neighbors as well. This is known colloquially as routing by rumor. For every other node, each node is going to determine the lowest cost next hop. The algorithm is going to run simultaneously on every node. And so how does this work? For example, node E knows its cost to its neighbor. And so node E, the cost is going to be 5 to A, 1 to B, 3 to C, infinite for D, and 1 to from E to F. And so if we have our distance vector here, we can have node E is going to listen to messages from its neighbor. And so A says it has the following routes: 0 to A, 5 to E, 2 to B, 1 to C, 4 to D, and 4 to F. So node E is going to look for each route from each neighbor in. And so it's going to add its cost to get in to n's cost to get to each other. And so for each node, if the sum is lower than the cost than what E has in its route table, E is going to change its own route to run through the neighbor. So reviewing nodes A messages, 5 plus 2 to B, 5 plus 1 to C, 5 plus 4 to D, and 5 plus 4 to F. Only 9D is going to be considered less. So we'll set the next hop to A. So D is going to now have a hop of 9 to A. So if we review node B's messages, we have 1 plus 2 to C, so in this case, we have 3 to A and 5 to D are going to denote lower costs. So we'll set their next hop to B. So if we review node C messages, we have 3 plus 1 to A, 3 plus 2 to D, 3 plus 5 to F, and 3 plus 2 to B. So none of these provide for a lower cost. We review the routes for node F's messages. We have 1 plus 5 to C. We have 1 plus 1 to D. We have 1 plus 2 to B, and 1 plus 4 to A. So 2 to D is going to be a lower cost. So we'll set the next hop to F here. So with this in mind, do you agree that E knows the next hop for the lowest cost routes to other nodes? This is under the assumption that the other nodes knew their lowest cost routes. So when this runs on all nodes simultaneously, they will converge on this solution, and it takes a relatively short time for this to occur. There are other algorithms that can also take into consideration, in that we have hierarchical routing algorithms. These algorithms are used for networks of networks, and they represent networks that are very large in scale, and they can have frequent state changes. With this in mind, we want to compartmentalize so the routing information protocol issues don't spread and cause widespread outages. So a prime example of this, of course, would be the internet itself. With this in mind, we can have an autonomous system is going to represent a collection of IP routing prefixes under the control of common administrative policy. This presents a common and clearly defined routing policy to the internet. Gateway nodes can connect to the autonomous system gateway nodes for inter-AS routing as well. And so here we have an example of how hierarchical routing can occur. And so in this example we have our autonomous systems assigned by numbers. Then we have our nodes within an AS that can use LS or DV for the appropriate routing as well. And then we have our gateway nodes that are using our border gateway protocols to interconnect the autonomous systems together. So here we see connections occurring between A, G to CG1, CG2, and BG. And so in this, we can see that nodes within our autonomous system are going to either use an LS algorithm or DV algorithms in order to, or some other routing protocol can be utilized in order to transfer our messages. And so with each one, we can use the link state algorithm and follow those specific steps, or we can use the distance vector algorithm. We will use our border gateway protocol as the internet inter-AS routing protocol in this case. Some specifics associated with border gateway protocol. It's important to keep in mind that BGP is a path vector protocol. The gateway routers will send path vector messages to advertise the reachability of networks. Each router that receives a path vector message must then verify the advertised path according to its policy. So if the message is compliant, then the router modifies its routing table and the message before sending the message to the next neighbor. It then modifies the routing table to maintain the autonomous systems that are traversed in order to reach the destination system. It can then modify the message to add its AS number and to replace the the next router entry with its identification. So an example, if we're routing at Georgia Tech, we have communication among the nodes in the autonomous system. We have an intra-AS routing protocol that utilizes this. And then we also have inter-AS routing protocols for communication among nodes across the autonomous systems. These are all represented via a routing table. And then we have our layer 3 network protocol, layer 2 link, and layer 1 physical. The GT campus network is going to be an AS2367, and there are 2 Juniper routers that function as gateway routers and run the border gateway protocol. The rest of the campus network runs OSPF, and that is a link state protocol. And so if you recall, we had a example earlier where we denoted Joe sending an email to his grandmother from Atlanta to Yuba City. So in this, we denoted a core of the internet. And so what exactly is the core of the internet? Well, really, there isn't an internet core. We have dozens of internet exchange points that are utilized by internet service providers. And this provides for an interconnection of our networks. And so various ISPs can be interconnected together to provide for communication and the transmission of packets. And so this is basically making use of a layer 3 partial mesh topology. And so considering that there really is no internet core, you want to consider the ISP peer or using bridge gateway, border gateway protocol, such that all the gateway routers know multiple routes to every regional ISP. You can begin to see that the internet has a highly distributed core created by multiple IXPs. And so you can, there are going to be at least 4 internet exchange points in Atlanta. GT participates in and operates an ISP. SOX provides network access for about 3 dozen Southeastern universities and research centers. So here we have an example of a diagram that shows the interconnection of various research institutions. And so you'll note that the traffic is allowed to traverse through the network to get from one ISP to another. However, the diagram is not going to show any peering entities such as Google, AT&T, NASA, the Department of Energy, or Comcast, or other groups. So here we're able to see the interconnection between various institutions in Tennessee, throughout Georgia, as well as Alabama, and how they use internet exchange points to interconnect one another. So in this respect, we have wrapped up understanding the network layer within that is utilized for transferring data packets. Some key terms that we've discussed are circuit switching, packet switching, message switching, understanding switches and routers, input buffers, output buffers, as well as the routing table. We've also understood other terminology such as delays, store and forward, queuing, packet loss, understanding service models, virtual circuits, as well as datagrams. So in summary, you want to we've discussed the various layers for the OSI model, where we have sockets that are utilized at the application level. RPC is utilized at the presentation layer. TCP is utilized for our session layer. TCP is also utilized for our transport layer and combination. IP is utilized for our network layer. And Ethernet is utilized for our data link layer. And then for our wired or wireless hardware layer, it's utilized by our physical, for those physical interconnections. So this provides us with an overview of understanding the various layers and how they interconnect together to provide for appropriate networking and modern network systems.